No.
I'm doing the best I can. This is actually early. Normally we're 10 minutes late, so. Noon. I know.
Hebrew, this says, may I help you? It's a rude way of saying, may I help you?
Huh? What is the polite way? There is none.
Hebrew, no, it doesn't exist.
Yeah.
Now you have to translate.
So, but
Here, I'll make amends by erasing the board.
yeah, and also I need to make sure that it's the right. This is the one that has HDMI, right?
You need to turn on the projector. That might
Well,
help
and I also have to put it to the HDMI, right?
push on.
Push on, okay. It's in English, I'm sorry. On Saturday, I'm looking for a guy's house, and I asked two little kids, "You speak English?" They go, "Yes, I'm looking for this house." They go, "What is the name?" And I go, "Eisenberg." They go, "It's right there on the mailbox, Eisenberg," in Hebrew. So I don't know.
They're saying there's a Dowling invariant of starting 10 minutes late, even when you come on time.
Well,
You have to be late.
he blames me. Heisenberg.
Oh, Heisen.
Oh, Heisenberg. Oh, Heisenberg. The pipes are calling. I'm going to switch it to the HDMI.
And then there's the record button.
But I need the microphone.
Come on, high maintenance.
Well, I didn't want to use it, but a guy says that
What are you waiting for?
we have to put the microphone.
Oh yeah, you do. Is it already recording automatically?
No, you have to press הקלטה.
No, because, no. So you,
יש פה...
part of, I know, but they said it's configured from far away. No, you don't have to touch anything. So press it anyway. When you start talking, press this the record, the button here.
You think?
Just to be sure. If it didn't start to record by itself, it didn't.
It's not working. Is it working? Make a full.
A fool?
Yeah, make a full.
I think it's working.
Stick that somewhere.
Where the sun doesn't shine.
Now you have to also project.
Yeah.
Is that going to happen?
Well, is it on the HDMI?
HDMI. You have to push HDMI for
Well,
it actually to work. It works.
That's why you're here, Kat.
Yeah.
That's why I pay you the big bucks. Yeah, there's no screen.
There is.
That's the screen?
It's a screen.
You added some decoration. To
Nothing comes out of the ceiling. I didn't even
Can you
know.
please press the record button? The red circle.
The one above it. The one that has a...
And the light should turn.
Is it lit up?
Blinking red.
If it's blinking, don't touch.
אייזן. אתה שואל אותי?
אייזן זה לא זה.
זה מה שאמרתי לו. אייזן בטון.
Blinking red.
Yeah, it's good.
Okay?
צורך כן התחיל לך, זה לא בזמן. לא, הוא לחץ. הוא לחץ.
באיזה זהב?
This is the American Sunday.
You're taking a picture of this?
John, we are on Monday today.
All the slides are here. You don't have to take pictures. Okay. Oh, you only want that. I thought I sent this to everybody, but apparently not. Okay.
Only the register.
Okay.
No, the register didn't get it as well.
The register didn't get it either.
Send the link to the files themselves. Not to the
Yeah. Okay. So, suppose I have a probability distribution, okay? A probability distribution, a classical probability distribution, okay? And I am trying to measure, so, what am I measuring? Phi, right? So this is phi, and it's peaked around phi, right? And so I want to that's the underlying thing that I would like to measure. Now I would like an unbalanced estimator. So in this room, I would like a balanced estimator. The room is unbalanced, right? Because the peak of the distribution is somehow way over on this side. That is an unbalanced estimator. Okay, so a balanced estimator means, so what am I doing? I have a device. We've already seen this. We've taken, this is my source, this is my phase shifter. All right, and then this is my detector scheme. So, what do? I send a probe. What is a probe? One photon, an entangled photon pair, a Newton state, whatever you want. Usually when we talk about the probes, I talk about my resource, fundamental resources. Each photon counts as one resource or interrogation, to be fair. So but let's do the classical case first. I just send single photons through the interferometer. So I send the first single photon, I get a data point, click, okay? So now that's data. I would like to estimate phi with this. Not going to be doing a very good job, okay? So now I send another photon, but because there's fluctuations, even the quantum ones, I get another guy here, okay? So now I can say, well, if it's an unbiased estimator, unlike this room, if it's a biased estimator, then I would really need more on one side than the other. I could say, maybe it's midway between the two, okay? So I get the beginning of an estimate. So I should not ask this. Everybody knows Bayes' theorem. Bayes was an Irishman, I think. So Bayes' theorem says that...
Nobody's perfect.
Nobody, I know. Well, he was a Protestant, so it's not exactly the real Irish.
It's half Irish.
Yeah, he's not the Catholic one. So Bayes' theorem says when I estimate something like this, I have a probability I have a probability of this unbiased estimator, and then I have one data point is not very good. Okay, then I get the second data point, and I update my estimate of where the true probability distribution is and the mean and so on. And as I get more data points, the Bayes theorem, and again, I'm not doing a lot of the math. I give links to folders in there, which nobody has now, to the papers, which has all the math in them. But I'm trying to give an intuition how this works. So then, so I get another data point. Okay, so I can update my estimate using Bayes' theorem with the other data point, and then I get over here, and I get over here. So this is the true phi that I'm trying to measure. So the phi with the hat is my unbiased estimator. As I take more and more data, this becomes closer and closer to phi. So it's not an operator. So, and so with the Bayes' theorem says, okay, if I take an infinite number of data points, then my estimate of phi becomes equal to phi, but I don't have the luxury of an infinite number of data points. Even in Nadav Katz's lab, at some point the graduate students graduate and you stop taking data. Okay? So then the real question is that if I have n data points, or n photons in this configuration, how good can I do? That's the whole estimation problem. We've been talking about shot noise limit, Heisenberg limit, but it all boils down to if I have n probes and I send them through this device and I try to estimate phi, how good can I do? Okay. So that's the theme of today's lecture. Can I lower the... I'm getting feedback. Where's my clicker? Okay.
There's a button there that can mute you.
Yeah.
Can you take it out of your pocket for a second? There's the clips you can... Should be volume.
Just turn it down a little bit. I don't need it, but the recording requires it, so...
There's mute. So just put it a little bit further from your mouth, maybe.
יש על הפודיום לדעתי.
Nothing. On the old ones there used to be.
Okay. Well, I think it's only when I talk directly into the thing like this.
Yeah.
I won't
I think
do
it's
that.
when you move over there.
Oh, there is one on the podium. Here.
Ah.
This one. Do אני משפיע? השפעתם?
Let's go.
It was too...
Maybe go over there. Go over there.
No,
Ah.
So, זה בסדר.
Okay. You can tell I have opera singing training, which is great for teaching class. Okay, so this is the whole thing. How many points do I need to get a particular accuracy in measuring the phase? Okay, and I never get perfect accuracy. What the accuracy scales with the number of data points. This is intuitive. If I go into the lab and I'm trying to measure a distance with a ruler, I make many measurements and average the results. And classically, it always goes back to 1 over square root of n. Okay, there are many ways to look at this. You can think of it in terms of Poisson noise, the law of large numbers, but you always get this 1 over square root of n. Okay.
Sorry. Phi here, not at. Phi is a distribution or a...
Phi is, this is,
Phi hat, you need like a flat bar or something.
this is the average phi. Okay. Better? And then, I'm stealing these photos from all over the internet, so sometimes phi is phi bar, and then it becomes theta, and then it becomes theta hat, so you just have to keep up. Okay, but I didn't have half of Hagai Eisenberg's whiskey allotment yesterday, so this should be, but it's a little bit more mathematical. Okay, so here we are. Classical and quantum parameter estimation. Blah, blah, blah. Wow. Okay. So let's, this paper is online, but I'm going to do a little bit before I get to this. So we start to discuss this Heisenberg limited parameter estimation in this paper, and then I give you Kaushik's PhD thesis, which is like a book, which has the full quantum Cramér-Rao bound derivations and everything in it. So I will just sort of sketch this. But this is what I have done here. And so, like I said in the first lecture, many pens needed. Green. One of the things that we like to do, and it's an easier measurement to make. So one measurement that we talk about is that there's a fixed probability distribution and I'm trying to estimate that. And that takes a lot of data. Okay. But if the probability distribution moves, that's easier. LIGO doesn't care what fringe it's on. It just wants to know if the fringe moves. That's the gravity wave. So this guy here is now going to be, well, this is phi of 0. And then this is phi of theta, of phi, okay, which is moved. And then delta phi there is the minimum shift that you could detect. So if it moves, I want to know by how much. And this is like the Rayleigh diffraction criteria where you have two objects, okay? And if they are too close together, then you can't tell this peak from that peak, okay, unless you take a lot of data. So there's a connection between the two things. So this is what we're trying to do. Okay. So there's a relative phase difference delta phi that renders the two quantum states distinguishable, and delta means it's the minimum one. So that means the state here and the state here are orthogonal. And that's the easiest case that you can have. If it moves so much that the two quantum states are orthogonal, then you can see this quite easily. Okay. So hence we assume the dependency does render phi orthogonal, and then we can minimize delta phi to satisfy equation 1. All right, so this is the sort of half-assed calculation. So they do the minimization process. This is in the paper with Peter Koch. And we get something that looks like this, okay? And you've seen this before. X is the thing that I'm trying to measure. And I called it M before, which is the intensity differencing, but now it's an arbitrary Hermitian operator. And so I have this funny derivative in the denominator, and then the fluctuations here. And then this gives you the minimum delta phi that you can pick up. And I'm focusing on the point, not I'm trying to estimate the stationary distribution, but it shifts by a little bit. Okay.
What you are trying to, you are measuring X and you are estimating phi.
Yeah, that's
So what you are trying to measure is it, when you're trying to measure, you mean phi.
I'm trying to measure phi. Right. But I actually, my data is X.
Yes.
Right? So the question is, and I don't have an infinite number of data points, okay? So, and the data in the X, the data has fluctuations in it, and typically I'm ignoring classical fluctuations from the laser intensity fluctuations. I'm only thinking about quantum here. So when I'm doing classical parameter estimation, there's a limit on how much these fluctuations can be. Okay? So if I'm doing, and we've mentioned this before, if I'm doing Mach-Zehnder interferometer with classical laser light has no fluctuations, okay, in principle. And so delta X is 0, and I can measure the phase with infinite precision, okay, classically. But in quantum mechanics, we went through this the first week. The electric field fluctuates, the intensity fluctuates due to the shot noise, the vacuum leaking in the unused port. So this thing is never 0. And then the question is, how small can we make it using entanglement tricks or not entanglement tricks? And this thing always shows up in the denominator. Why does that show up in the denominator? Okay. Because that's the slope. And remember when I had my interference fringes and I said, if the slope is very steep, I do better, right, intuitively. Well, the slope is dx d phi. I want that to be as large as possible in the denominator to make delta phi as small as possible. So that's the intuition behind that. So when I derived this the first time, I gave a calculus 101 approximation with differentials. Okay. Now we're going to do a little bit better because you might not necessarily believe that. Okay. So this is the first stab at this. So Mandelstam Tam, okay. The Heisenberg uncertainty principle for X and P okay. This you can derive because X is an operator that is conjugate to P, right, which is not equal to 0. X and P don't commute, okay, and that's where the quantum noise comes from in the ground state of the harmonic oscillator. So I have the ground state of the harmonic oscillator. This is X, looks something like this, and delta X times delta P is greater than or equal to H bar. But then I introduced the energy-time uncertainty relationship, and that is a different beast. Why? We have a perfectly good operator for the energy. It's called the Hamiltonian. Okay? But we don't have a time operator. That does not exist. Okay? So, equivalently, you remember I rewrote this in terms instead of energy times time is greater than equal to H bar. I had a delta phi times delta number is greater than 1. I derived it from this. So that's having a time operator is equivalent to having a phase operator. Let me write it over here so you can see it. We have a number operator. That's just A dagger A for the harmonic oscillator. And so if I had a phase operator, and this is greater than equal to 1, not equal to 0, yeah, fine. Away we go. Well, we don't have this. For the same reason we don't have that. I actually derived this from that. So there is no convenient phase operator. Okay? So I can't just lift this formula and apply it naively directly to energy and time. I have to do something a little different. Now there's two approaches. One is you try to construct a phase operator. So back in the 90s there was an entire industry of making phase. So there's the Peg-Barnett phase operator and the Barnett-Peg phase operator, and they're not even the same thing. Okay. They don't give it. So every guy is coming up with their own phase operator, and this is the road to hell, because you can construct something like a phase operator in some limit. It becomes, you get the right answer, but you get extra additional terms, and I don't want to use a theory that I cannot compute and get a number quickly. I'm a lazy theorist, remember? Hans Bethe once said, the job of every theoreticon, the job of every theoreticon is to produce, at the end of the day, a number which you can compare to the experiment. And if you're not doing that, you are not doing your job. Okay? So string theorists, they produce. Well, I used to think string theory was a theory of everything that predicted nothing. But Ephraim Steinberg said, no, it's a theory of nothing that predicts everything. Okay, but at any case, you don't get a number out at the end of the day. And with the phase operators, you can get some numbers out, but it takes more than a day. And so we're going to take a different approach. So this is related to something called the quantum speed limit. When you have a Hamiltonian evolution of a Schrodinger equation, the Hamiltonian tells you how fast the wave function will evolve, right? It's always something like e to the I. This is the evolution of the wave function. And so it's guided by this operator, but time is not an operator. What is that constant?
Y bar.
It's Dowling's constant. Okay, so H bar.
1 over H bar?
Yeah, exactly. So I actually have a
Minus.
I have a LaTeX that rotates H bar by 180 degrees. So if you want to put Dowling constant into your paper. So the reason I like
Minus.
there's a minus. Ah,
That's good, minus.
thank you.
Plus.
Minus. Okay. But this is essentially the speed at which the Schrodinger equation evolves is guided by the Hamiltonian. Okay? So there is a connection between energy and time, but it's not this. With the operator, there's no time operator, but there's a speed limit on how fast a wave function can evolve, and that speed limit is controlled by the Hamiltonian. So we're going to get at the energy time by a different route. The reason I like this is because what is this constant? Oh, who is named after it? Planck. Okay. Who is that constant? Dirac. So Dirac got his own constant by dividing by 2 pi. So if Dirac gets his own constant by dividing, I can get my own by doing this. It's just as good. Anyway, I put this in the publications, and the editors say nothing, but they rotate it back. But it's very nice because often when you're solving the Schrodinger equation, you have e to the I and some horrible square root of blah, 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 all over H bar. So typesetting becomes much easier if you have 1 over H bar. You can just put that out front. Professor Eisenberg.
The way
Heisenberg.
The way I understood Mendelssohn Tam is that it's a relation between the accuracy you can measure energy to the time it takes you to measure. So the Hamiltonian, how is that related to your interpretation?
Well, so it depends on how you want to pitch this. So if you read this in Griffith's quantum mechanics, he calls it the quantum speed limit, as does Seth Lloyd, but we're not allowed to speak of Seth Lloyd as of yesterday. And so the point is that, when you're talking about, imagine this as a pulse now, evolving, a Schrodinger wave pulse, right? It only can evolve as fast as the Hamiltonian tells it to evolve, right? And so when I say, is the pulse here or the pulse here, and I want to know the difference, well, that speed is given by this guy.
That's not the uncertainty in energy.
Well, you get the uncertainty from energy from doing exactly that. It's in Griffith's chapter 2. Okay. So you get exactly this kind of result. So then I'm not going to derive it because this is not Quantum Mechanics 101, which apparently Professor Eisenberg has not taken, I teaches it, right? But
I'm teaching
Google Seth Lloyd quantum speed limit, and they talk about this kind of stuff. Okay, so how you want to interpret it, I just think, again, this thing moves, we want to tell if it moves, okay? The speed at which it moves for a quantum state is guided by the Hamiltonian. Hamiltonian is the total energy of the system. You put this all together and you get the phase shift, omega times delta t is greater than or equal to this. So it comes out of this Mandelstam. And I derived something like this using some half-ass calculation, but this is a little bit. But notice down here, this is the spread in the energy. That's what I'm after, right? The uncertainty in the energy is downstairs. So the bigger the spread in the energy, the smaller the delta phi. Okay? So the point is if I'm using classical like states, like coherent states and a Mach-Zehnder interferometer, and I inject vacuum into one of the ports, there's a limit on how much this delta E can be. But if I start playing tricks, so noon state, okay, noon state is a good example. I have 10 photons here and none here. 10 photons have an energy of 10 times h bar omega, okay? But it's a superposition of 10 times h bar omega here and none here. That's a huge spread in energy. Delta E is very, very large, which is why noon states do so well. But if I have a coherent state, the energy here and the energy here is almost the same. The spread is very small, and I get the shot noise limit. So having large spread in energy is the critical take-home message. How you want to interpret this is, I like the speed limit because that's what I'm after. This is moving, and I want to know if it moves. So I need to know how fast it's moving to be able to estimate it. Okay, so this is one way to look at this. And so you can compute quantum mechanically now the delta E, okay, and you get delta E squared is equal to E squared. This should really be the Hamiltonian, but I told you I'm lifting this from all sorts of different sources. So this is E hat operator squared, Hamiltonian squared, minus Hamiltonian expectation squared. Okay? And so the question is, what kinds of states can we make so that that delta E is as big as possible, noon state, I just gave you an example, to make the delta phi as small as possible. And it has a geometric representation and blah, 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 blah. Okay, so if you don't do anything, so we take this Mandelstam-Thom formula, which Professor Eisenberg is going to apparently argue endlessly about with his neighbor. So you agree with the formula?
My source of Mandelstam-Thom is
Griffith? Okay, so it's a quantum speed limit. That's my source too. So we'll just disagree on the interpretation. So Haggai tells me this joke about a Jewish guy is stranded on a deserted island and for 20 years. And he builds up a farm and everything to survive. It's like Tom Hanks on Castaway. And so finally they come to rescue him, and he's very proud to show he has a farm and he has a house and water plant and everything. And two shul, synagogue, okay? And they say, why do you have two synagogues? He goes, well, this one I go into, that one never. So it's the same with the interpretation of the Mandelstam-Thom. You know, that interpretation, never. Okay, fine. So if you look at states, coherent states are, okay, this is written some time ago. Now we know, if you go back to the Mach-Zehnder interferometer. Now here's my Mach-Zehnder interferometer, okay. Let me do the real one here. Am I allowed to write here? I guess so. So remember, if you put anything in here, and you put vacuum in here, you always get the shot noise limit, okay? We have a proof. This can be mixed, it can be pure, it can be whatever you want. With vacuum in here, you always get the shot noise limit, which reinforces this idea of caves that the shot noise comes from the vacuum fluctuations. So it says here, when coherent states are used, delta E is always given by this. So when I use any state, it doesn't matter, and I mix a vacuum on the other port, delta E is always given by this, where this is the mean number of photons for that state. So that's a much more general statement. There's nothing tricky you can do by playing with this state. It always gives you the shot noise limit. And the pi over 2, well, didn't we set pi over 2 equal to 1? We said 2 equal to 1, so it's just 1. Okay. I don't care so much about these factors. Okay, so when you're doing this kind of, so when I first derived the Mandelstam-Thom limit, I did something with the Calc 101 approximation with differentials. But the cheat was that when I did the Calc 1, I said that the quantum fluctuations are same as some kind of classical fluctuations. So you get the right formula, but the logic is not right. So this is a slightly better computation with truly with the quantum fluctuations. Okay, but then phase instrument, and this indication was the indication was that the phase instrument could not improve beyond the so-called Heisenberg limit, and so we've seen this before. Okay, and so the question is, can I do better than the Heisenberg limit? You know, why is that the ultimate limit? So remember, we had the paper, blah 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 Heisenberg limit, and I went to Burnett and said, how did you? Where did this come from? He goes, well, we just made it up. Okay, where they said the fluctuations could never be bigger than the mean. So you could actually beat the Heisenberg limit, but just by a little bit. So the question is, why is the Heisenberg limit truly the limit, or Heisenberg scaling? Okay, so back to our qubits. We're sending the qubits. This could be a clock, 0 and 1. It could be the upper and lower arm of the interferometer qubit. Remember, the Rosetta Stone says it's the same thing if the mass is the math is the same, if the mass is the same, but the math is the same, the physics is the same. So let's review this a little bit more detail. So now I'm taking my qubits, single qubits, and I'm sending them through the interferometer one at a time. Okay, and they all look like this. So here's some fancy notation, but I'm going to measure this using an x measurement. In x is the direction on the sphere. And each guy gets a cosine theta. If I have a bunch of independent guys, n of them, I get n cosine theta, phi. Theta and phi, remember theta is equal to phi because different people use different ones. Okay, so if I take independent qubits, the best I can do, you run the numbers, you take the Mandelstam formula, the x, the observable now is sigma x, okay, and you calculate this and you get the shot noise limit. So this is another proof that if I don't do anything fancy, I don't correlate the particles. These are quantum, these are qubits, right? These are quantum. I'm going to hoist myself by my own petard. These are quantum states, but they're not entangled. And so if I send unentangled quantum states of any kind through any interferometer, I always get 1 over n, square root, okay, for shot noise. So that's a separate proof from the Mach-Zehnder in qubit language that 1 over square root of n is the best you could do without correlating things. All right, but we've seen this before, right? With the help of quantum entanglement, we now know how to make noon states. So we can do this with either the Mach-Zehnder, or we can make the noon G8Z states in the clocks, okay? And we get this factor. This is the magic thing, okay? Here, when the n shows up there, okay, and that gives me shot noise. I need the n inside the cosine for it to oscillate n times as fast. That's my super resolution. That's my super sensitivity.
So, John, what's that operator? The K1, K equals 1 to n. What is that?
This is the detection operator is we're making a sigma x measurement in the block sphere. And this is a tensor product. You could put a capital pi there. So I'm just making a sequence of x operator measurements independently of each other. Peter Koch, my PhD, he was my postdoc at the time. He gets fancy with the notation. I would have used the capital pi for product.
This is a sum, not product.
This is
the sum, not a,
this is a sum.
It's not like a chronicle product.
Yeah.
It's
It does look like a plus sign. Let me
like
think.
when we are doing
Yeah. Oh, no.
angular momentum.
I apologize. Replace it with the sigma. Okay. So, and obviously, if I add up n independent guys, I get an n. Okay. And then you get. So this says if you don't do any correlation, you recover the shot noise limit 1 over square root of n. But then we see now when I put the n here, right? Okay, and then I have the G8Z or the noon state. I can write this G8Z state. So this is important. Why is this important? Good question. This is my attempt. Remember, we have the block sphere for a single qubit, right? There is the equator and the qubit. And this is the ground state. Oh, there's a computer scientist out there who I will hate forever for doing this. But remember, we pop the qubit from the ground state into the equator, and it oscillates with the frequency omega t for the clock, kx for the LIGO interferometer. So the nice thing about this GHZ state is you can think of this as a giant block vector. So in terms of angular momentum addition, I've just made a block sphere where this arrow is n times longer than the single qubit. Okay? So this arrow, instead of being some length L, is just now n times longer than before. I don't know how to draw this. And as it whips around the equator, it's going n times as fast. Okay? And so this simplifies the analysis because you can now treat this. I'm going to kill myself on this because
Cast it over.
it's string theory. Oh my God.
Cast it over
I'm
your
entangled. Yeah. No, I would rather just keep doing this endlessly for amusement for the audience as he looks at his watch. The nice thing is when you write it this way, it looks like you're just looking at one qubit, which is easy to analyze, that's oscillating n times as fast, okay? And then you can write down a projection operator, a non-local observable sigma n. There are different operators that you can use. We call this the Ono noon operator, which projects into either the noon state or the Ono state, okay? We now know parity is actually the best thing to do, but this is an operator that gives you the right answer. And it's a non-local operation. When you run the numbers and you see the n has moved from the outside to the inside, which is exactly where we want it, okay? So instead of having n independent qubits, I have a big whopping qubit that moves n times as fast. You run the numbers for the Mandelstam equation, which is from Griffiths. That one I never go into, okay, and you get 1 over n. Okay, so entanglement gives you this precision. And the question is, can I do better than 1 over n? So there was a crazy paper by Shapiro came out in the 90s where he said you could get 1 over n squared. And then I wrote a crazy paper saying, well, if he can get 1 over n squared, then I can get 1 over n squared. This is before we had any idea what was going on, and we just made up states and hoped we could do better than the square root of n. But then Sam Brownstein and Carl Caves wrote a paper sort of cleaning this up and says, well, you know, your 1 over n squared is you're making measurements that are not allowed by quantum mechanics and this kind of thing. So if you do things properly, you always get 1 over n as the ultimate limit. Okay. So if you go back to Mandelstam, once again, you have this delta t looks like this. Okay, I think that's supposed to be delta e. That's a typo. Okay. So we know for noon states, for example, you get a delta E that is extremely large, all 10 here, all 10 here. So by the Mandelstam argument and the speed limit argument, it's always going to be something like 1 over n. Now people argue is there a pi over 2 there, a square root of pi, I don't care. It scales like 1 over n. Okay, so now let's do something a little bit more complicated. John Howell is here? Oh, good. Okay. He says, oh, you're doing quantum Cramér-Rao bound. And I said, I'm dead. He's going to inspect everything. So this is the goal. See if the thing has shifted. Okay, this is from Wikipedia. Always a good source. So this is the classical Cramér-Rao bound. And so how do we derive this? And I promise not too much math. This is the most math we're going to get. So it's a little, okay. But you have to have some math to do this. But I'm trying to give you some intuition. So let's go back. Oh, I erased my peak. So I've got the peak, and then there's some mean phi bar is a function of phi, and then I've got my dots. Okay, let's match the Wikipedia article theta. This is theta, and then theta hat is my estimator, right? From the data, I construct a theta hat, and if my estimation procedure is good, in the limit of the infinite number of data points, theta hat should approach theta bar. Okay, that's the goal of parameter estimation. So the theta bar doesn't have a bar over it, but the theta has a hat. And so now what we do, and I'm not going to go through this because it's a long, tedious calculation. It's in Kaushik's PhD thesis, which is 107 pages long. So it's in the folder, which you now can access. Please read it. Okay. But let's go back to the Bayes analysis. Remember the Bayes, the Irish guy. I make one data point. I estimate what the phase is. I do a crappy job. I only have one data point. 2 data points. I now update my information about what the phase should be, and I make a new estimate. So each step in the Bayes algorithm, I give a probability, a weight to the estimation factor based on the previous data, and I keep updating and updating and updating. Okay, so when you're trying to do this rigorously, one way to do this is to take your data and run Bayes' algorithm, okay? And you run Bayes' algorithm and you can get a better and better estimation of the phase. But this is complicated. You have to put it on the computer, run the Bayes algorithm. So remember, I'm a lazy theoretician, okay? So I don't want to do it all on the computer. So we make 2 approximations with the Bayes analysis, okay? One is the probability distribution is relatively well peaked. It's not flat. There's some peak that I'm looking at. That's the first approximation. The second approximation is that I assume I have an infinite number of data points, okay? We'll always do worse than that in the lab, but I want, instead of doing a computer and algorithm with my data, I want a simple formula, okay? Under those 2 approximations, you end up with this thing. So this is called the Fisher information. This is the number of trials, the number of photons, or the number of data points, okay? This is the expectation value. This is all classical, so the classical expectation with respect to an underlying probability distribution. The squiggly L is the log. Okay, so what is F? F of x is this function, right? The function of theta, and x is whatever I'm measuring. I'm measuring the sigma x or whatever, by data points. So it's very general, okay? Then, using those 2 approximations, you go from Bayes and you get the variance of any unbiased estimator. Again, this room is biased because there's nobody over there and there's a lot of people over there. I want it to be centered. Okay. Is bounded by the reciprocal of the Fisher information. And what is that? This is crazy thing, so let's go through this slow. Number of data points, classical expectation value, okay, and the derivative of the log of this probability distribution with theta and then the measurements in x in it, okay, which is called the natural logarithm of the likelihood function, which is f. And E is the expectation value. So let's think about this, okay. If the Fisher information, if you just look at this, okay, here's your Fisher information. If this expectation value is not too crazy, classical, then this is not, it's a logarithm, the derivative logarithm that doesn't change very fast. So all the action is here in n, okay? So the variance goes like this, ignoring this, it's just 1 over n. But variance is the square of the standard deviation, so immediately you recover delta theta is 1 over square root of n, which is shot noise from the classical parameter estimation. So you can play games trying to make this go slower and faster or whatever you want. Classically, you might get a factor of 2 there or half, but it's always going to be 1 over square root of n. Because there's not too many tricks I can do quantum mechanics in the classical world here, okay? And so the efficiency of the unbounded is estimated. And so the Cramér-Rao bound says this has got to be equal to less than 1. So if you run all of this crap through, you get this has got to be 1 over the square root of I. I is proportional to n, so it's 1 over square root of n. So the whole point of the classical Cramér-Rao bound is that you can't really do better than 1 over square root of n. So this is, at first I gave you 1 over square root of n with hand waving, and then I gave you the Mandelstam Tom. Now the Professor Eisenberg is asleep, we don't no longer argue. And then this is sort of the gold standard for classical measurement. Everybody says, well, we don't want to do the full Bayes analysis because that always requires a computer. And now, so you remember I told you about our magic, remember Gretchen, she showed you could beat the Heisenberg limit, okay. But that was with the Cramér-Rao bound, okay, the quantum one, which we're going to come up with next. And so to double check that, because there are approximations in the Cramér-Rao bound, an infinite number of data points for one, okay, and that it's well peaked. Well, the thing for the Heisenberg, beating the Heisenberg limit, it's well peaked, but the question was, do I need an infinite number of data points to beat the Heisenberg limit? So we went back and did the full Bayesian analysis. So we had simulated data, which is much easier to make than real data. And with the simulated data, we did an analysis, and with like somewhere around on the order of 1,000 to 10,000 photons, you actually beat the Heisenberg limit. So, because this assumes an infinite number of data points, the question is, where is infinity? And if it's 10 to the 30 photons, then you're cheating. So that's a few thousand. Okay, so, all right. Now we want to make this quantum. That was not supposed to be there. Okay, so now we go to Kaushik's thesis, and I thought I could make a lot of slides, or I could find his PhD defense, and then, because basically I want to talk about what's in his thesis. So you heard about the clocks, and we heard about the LIGO, okay? And with using entanglement, I've argued you can do better. Okay, so quantum optical metrology, a brief review. And we already seen this, but now I'm pitching it in terms of parameter estimation. I prepare my probe states, which are photons, but generically they're qubits in some representation that I send through the phase that I'm trying to measure, okay? And the dynamical process, well, this is just e to the I h bar t, where h hat t, but h hat for a phase shifter is just n hat times the classical parameter, the phase shift. So this is easy to write down, and so this is why the noon state gives you a nice result, because if I have one photon, I get 1 phi. If I have two photons, I get 2 phi. If I have three photons, I get 3 phi.
Without the t.
No, t. Good. Otherwise, the units are wrong. Okay, yeah. Phi is now taking the place of t. Yeah. So I could. So this was something that I didn't understand, right? Okay. So if I have a Fock state, okay, I have a Fock state of 10, and I send it through the phase shifter. What comes out is e to the I 10 times phi times the Fock state that I started with. So you get, this is why the noon state works, because it takes whatever integer is here and it sticks it up here, okay, in the Hamiltonian. So the struggle I had is that if you send a coherent state, you do get a coherent state as a sum over all of these Fock states, right? So coherent state is sum equals 0 to infinity, and you have the square root of alpha over the square root of n factorial, blah, 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 and then there's an n here. So each one of these, okay, gets an e to the I n, little n, and phi. So you might think, oh, okay, I got like noon state behavior or something like here because of the integers. But if you do the calculation, if you sum the whole thing up.
Alpha to the power of n.
Yeah, yeah.
But the square root. Alpha to the power of n.
This guy.
Alpha, numerator. Alpha
To the power of n.
Just changing alpha to alpha.
Yeah, I'm just changing alpha, but I'm not increasing the power of alpha. So
No, but the coherent state is alpha to the power of n.
okay. N.
And lower. Yes.
Okay, fine.
Without the square root.
I'm focused on this. Okay. So the point is that you get this integer phi, 1 phi, 2 phi, 3 phi, and you think, well, that's good. I'm getting something like noon states. But they all sum up. So if this is alpha goes in, what comes out is just alpha e to the I phi. All the n's cancel out, and you just get this. So if you're used to working with coherent states, you go, how can this possibly be? Because when I use a coherent state, I don't get anything. So that's why one reason why the Yerke state, the M&M state, the noon state, they're all Fock states. So they have a fixed integer number here, okay, and that's where the extra phase is coming from. Okay, so your dynamical process in this case is just the evolution, and then your detection over here, parity, whatever you want. Then from your data points from the detector, you'd start to estimate your phase. Okay, this is the mathematical procedure written out in terms of an operator. So interferometry with a coherent state, we already know, gives you 1 over square root of n. Okay, and the vacuum fluctuations suck. So this thesis is 2005. The proof that any state, we always write if you take coherent state and vacuum fluctuations, you get shot noise. And the proof that you take any state with vacuum fluctuation, you get shot noise. That's something we just finished like a year or two ago. So this was something we thought was in Cave's paper, but he never heard of it. So no matter what you put in, the vacuum fluctuations give you the shot noise. All right. So here we go. The squeezing approach, we already saw, plug the unused port. And now when this thing moves, you can tell better, and you get sub-shot noise precision. In the limit of infinite squeezing, you get the Heisenberg limit, but in real squeezers, you get a factor of 2 because you can't infinitely squeeze. Noon state approach is digital, but where's Kafir? There. Okay. As you said, well, now I only have 6 or 4, and so what am I going to do? It sounds like your experiment. Okay. So anyway, you lower the numbers, you can get this digital approach, and so this is where this e to the in phi in one arm versus e to the in phi not in the other arm gives you the enhanced resolution and sensitivity. And we, a lot of this is historical. I realize I'm standing up here and I can just sort of talk about stuff that seems familiar for me for the past 30 years before you were born. And then I realized you don't know the whole history. That's why I'm here. It's kind of in my brain. Okay, so we now know parity seems to be one of the optimal things. Now, what do we mean by optimal? Let's get to that. So using the Noon state approach or infinite squeezing, we get Heisenberg limit. And then this is the review of the Hoffman. Okay, squeezing, it doesn't get you too good unless I bring the squeezer down. So now I take the coherent state and squeeze vacuum, but I match the intensities. And you saw this before. This is from Yaron's paper. Then you get the poop is removed, and you get this supersensitivity. We'll come back to this scheme later. Okay, so now I just kind of reminded you where we were. So what are we doing now? Okay. So I'm now going to switch from the classical Cramér-Rao bound to the quantum Cramér-Rao bound. So the first part of the switch is easy. So this is some probability distribution, right? It's a probability distribution of x, which is related to the data points and the phase that I'm trying to estimate, right? That's my probability distribution. So the first step is pretty easy. If I'm working with pure states, then the quantum mechanical probability distribution is given by an expectation value of some operator with respect to the pure state. So I can always construct a probability distribution from a quantum state and then just apply the classical thing. If it's a mixed state, a noisy state, then I have a density operator, okay, that's associated with the state. And since not every, do you know what a density operator is? Okay. So the third year student knows what it is. So the density operator is a lot like a probability distribution. So if I want to take the expectation of some operator O, I just take the trace of the density operator on O, and that gives me the expectation, okay? So the point is I can construct a classical looking probability distribution always from the quantum theory, and then just apply the classical Cramér-Rao bound. And so you get the same answer, except over my shoulder. I think I'm going to end up hanging from the ceiling by my neck. Okay. So you get the same formula. Okay. You have the only difference is that the expectation, which was classical expectation from before, you replace it with quantum expectation, and that's the only first difference between classical and quantum parameter estimation. Okay. But now there's an important. So this formula, if you go back, What was I before is now F for Fisher information. What was N before is now nu, okay? But you get delta phi goes like 1 over square root of nu if the Fisher information doesn't give you anything fancy, okay? So if this is somehow independent of N, then you recover the classical result that delta phi goes like 1 over square root of nu, which is the shot noise limit. So I need something fancy to go on in here, okay? And the point is the Fisher information contains information about the fluctuations in the underlying probability distribution, but for quantum states like Noon states, we can have huge fluctuations that you can't get classically, so you get extra boost from the Fisher information, and so you can get Fisher information that's also proportional to nu, so you get 1 over nu squared, square root both sides, you get 1 over n. And you can kind of show, using the speed limit arguments and other things, you don't do better than 1 over n. But this is a long, a separate course, which I will teach next year. So remember, crazy Dowling and crazy Brownstein, no, it was crazy Dowling and crazy Shapiro cooked up a state that had a 1 over, delta phi is equal to 1 over n squared. We do better than the Heisenberg limit. And then Sane, Caves, and same Brownstein said, look, if you do this parameter estimation stuff correctly, you never get any better than 1 over n. 1 over n squared is out. You're basically, you're using a state that nobody can make in a detection scheme which is unphysical. So if you fix that all up and do the correct analysis, you go back to 1 over n. All right. So n is, nu is the number of measurements. And this derivative of the log we saw before, there's the probability distribution, and the expectation is here. So this is the quantum Fisher information is identical to the classical Fisher information, okay, with respect to some detection scheme. So what is lambda? Lambda is a detection scheme, right? Lambda is the thing that I deploy in Nadav's lab to get these data points. So this is, in classical theory, you have lots and lots of detection schemes, okay? And so this was the problem before. I'm going to do parity, I'm going to do difference, I'm going to do coincidence count, intensity. So each time I switch the detection scheme, I get a different result. If it's better than what Milburn published, I publish, and away we go. And then you can play with the states, and there's almost an infinite number of possible combinations of states and detection schemes, and so you can write lots and lots of papers, okay. So the wonderful thing about quantum mechanics, one of them is that I'm not going to go into too much detail, but you can say any detection scheme in quantum mechanics must have certain properties. It should be Hermitian, it should have eigenvalues that are, that don't go negative, and various other things to be a physical detection scheme. So you write down this definition of what a detection scheme should look like. And so these are called POVMs. I don't know why my lambda is so long, okay? And every detection scheme that you can think of can be written down in terms of an operator, the operator that you apply at the end of the day. So it could be A dagger, A, or A dagger, BB, or whatever you want quantum mechanically. Let me just finish this. Okay, fine. A guy's giving me the 1 hour break rule. So that's the critical thing. In classical mechanics, you don't have any uniform description of how to categorize all your detectors. In quantum mechanics, you say all possible detectors have a particular form, and I can write down an orthonormal basis for the detectors. So I can now say, no matter what detection scheme Nadav Katz rolls out in his lab, it's one of these I. And then I might have an infinite number of them. An interesting property is that you sum them all up, you get one. So I have to use one. I can use them in all kinds of different combinations, but I always get one. So that's the critical thing. I now can take any detection scheme and abstractly write it down as an operator. And then next we'll see what we'll do with that.
Drama.
He's taking a picture. Okay. 5:10? Yeah.
You have to start with
You're going to
all the European collaborators. I showed.
You're going to a meeting. Hello, European collaborators. Where's my water bottle?
John.
Ah! They're wondering who I am. Dirk!
They don't know.
I have not seen you in years.
I think the microphone is not working.
He's
anymore.
not seen you. You have less hair, Dirk. It's all gone. It's all gone. I know. Me too. Hi.
Something. Yesterday, you said that the dephasing is when we have a superposition, a single.
Yesterday.
Yesterday. A single state which is in superposition of slow, medium, and fast.
Yeah.
Maybe that was the dephasing. What is this? What is the degree of freedom that they are superposed on? Because we did the ground and the excited state. Okay, that is not the ground and the
Have you had Quantum 101?
Yeah.
Okay, so the first thing you do in Quantum 101 is you write a Schrodinger wave pulse, right? And in free space, so this is a pulse, all right? Okay. It's it's a pulse in time, right? So it's a spread of time, okay? But if you Fourier transform it, you get another pulse. If it's a Gaussian, it's the same width in some units. It's just delta omega, right? Okay. So you know if you're in free space and you have an electron and you release it, push it, even if we let it just sit still, it spreads because the Schrodinger equation is only first order in time. So for photons, the Maxwell equation is second order in time. You have a d by dt squared, no spread. You get photons in free space have no spread to them. But electron wave packets have a spread. As they move, they begin to spread. Okay. So now it's the same thing. Solve the Schrodinger equation for my qubit. Okay, it's a simple Schrodinger equation. But this still obeys an equation which is first order in time. So as it moves, it starts to spread, just like this guy does. Exactly the same thing. Now, the guy here.
In order to make a wave packet, so I have to make a superposition of different eigenstates
Right.
of the Hamiltonian.
So when I make
So is this different eigenstates of the Hamiltonian, or these are all the same energy?
okay. So when I make this, the minimum packet I can make is delta x times delta p, right?
Yeah.
Okay. So when I write this arrow, this is cheating, this is classical, okay? So whenever I have an angular momentum state on a sphere, I actually should draw a blob, okay? And the state,
So also
they have a,
crowd and
yeah. And this comes from delta jx times delta jy is always greater than and equal to jz, the angular momentum, okay? So I didn't go into this, but when you write down the equation for anything on a sphere like this, there's an uncertainty blob, okay? And that's what's spreading. That's what's spreading. Now, when I say dephasing, different people use different terms. So in the NV diamond center, the larger effect is the NV diamond. This is my NV diamond, right? Okay. And it spins around to measure the magnetic field. In the NV diamond, they have, here's my NV diamond center, right? Okay. But there are all these other carbon atoms. In diamond, it's carbon, right? So this one, you want it to have a spin 1. The NV center has a spin 1, okay? Well, you don't want any of these guys to have spin, because that's going to cause a dephasing. But it's not the dephasing inherent to the Schrodinger equation. It's a dephasing induced by coupling to the environment.
It means that I've neglected some terms in their Hamiltonian.
Yeah, I have to. So what's happening here? So now I go buy diamond. I go to the diamond store, and I say I want diamond that's isotopically pure, spin 0 nuclei. I forget which carbon it is, and they go, "Oh, that's going to cost you." Okay. So 1%, if I get 1% of the bad carbons, okay, that's $1,000. If I get 0.1%, that's $1 million. So if I get 0.01%, that's $1 billion. So the problem is you can't get it isotopically pure. So what happens is some of these guys have spins, okay? And this particular singlet kind of transition, these guys with just thermal fluctuation will flip at the same rate of the fluctuations of the thermal bath. And that gives rise to fluctuations on my NV diamonds, and this blob becomes much bigger. So in quantum computing, we call this decoherence, but in NMR, they call it dephasing. They don't care where it comes from, okay? So this is the much bigger effect at first. So what do? You try to pay for more expensive diamonds, or you cool it. If you bring the envy diamonds down to near millikelvin temperatures, this goes away. Yeah, but I want to make a hat that I put on my head at room temperature and sell it to iMod that measures my brain waves and I can read your mind. Okay, this is a CIA program to do exactly this. So the guy doesn't want to talk. You put the hat, read the brain waves, and see what he's thinking. I'm not kidding. Okay, so
if he doesn't say anything, then you begin to cool it.
Yeah, no, we're not talking about that. Yeah, okay, you into the pool.
If it's a man, it cools down. If it's a woman, it burns up.
Yeah.
He thinks about everything.
But yeah, so the point is that this is going to run at room temperature. So if you run at room temperature, you have the dephasing. So when I'm applying the decoupling pulses, I'm actually protecting against this larger dephasing from the spins. I'm nowhere near this Heisenberg limited thing. Okay, so when you see all of these oscillations dying down, the frequencies are not the Heisenberg limited frequencies of the Schrodinger equation. They're these frequencies that are coming from the back. Okay, and that's critical because I can't really do much to control this. This is already Heisenberg limited. But this, I look at how fast are these guys flipping? What is the spectrum of this? And then I design pulses that attack this noise. I want to get to that, the Heisenberg limited guy. But even at the Heisenberg limit, you can play games. You can squeeze this, and this is another approach. Okay, so I take this blob, which is a circle. I'm going to draw it like this. Okay, and I squeeze it and put it into the equator. So now in the equator, it looks like a banana. So this is called spin squeezing, but I can do this with a single qubit at 0 temperature. I do this in the ion trap.
Or to have additional field outside magnetic field.
Well, it's not so much addition. To make the squeezing, you have to do something pretty tricky. But I'm just going to measure so I'm not telling you how I do this. I have some sort of operation there. But now when this guy spins around, right, it's measuring the phase. The minimum detectable phase is the width of the banana. So if I squeeze it, I don't care about what's going in this way. It's exactly analogous to squeezing in the LIGO. So as it spins around, my delta phi, I can actually make the delta phi small at the expense of some other parameter going up. Okay, so this was one of the first experiments by Wineland, and they use it in the clock. At the clock, they want to measure the clock work, so they squeezed it, a single qubit, and then they get more accuracy that way.
So, if I understand the whole thing, so even if you do the Cramér-Rao, whatever you do, then it really doesn't depend on the operator that you're measuring, but it does depend on the model of the noise.
Yes.
And the probability.
So that's what we're going to do
also,
next.
when you try to optimize your probe, it really depends on the noise. So the whole physics is really learning the noise of the thing.
Well, that's but when I talk about this, there's no noise. This is just the natural spreading of the wave function.
So we have
it's a quantum noise. The quantum noise.
Quantum noise, which is uncertainty.
And
there is the noise, which is really the lack of knowledge
of what
my ignorance is the noise. I cannot model this whole thing, so I can make it Gaussian or whatever.
Right.
So this is when I'm trying to model my ignorance.
So
I call it noise.
I have my army project is you put an additional spin here, which is called the sensor qubit, but we're not sensing anything. The sensor, we send pulses at the sensor qubit. It measures the noise in real time, and then because it might fluctuate over time or whatever, and then we apply our pulse sequences. We design our pulse sequences with machine learning algorithm, and then apply it to the computational qubit to fix it.
The noise from
we have another qubit that measures the noise.
And then
So this has to be a different isotope because it needs to decay much faster. If it decays at the same rate as this, you don't gain anything.
And it change on time. Change on time.
Yeah.
So you have to update all the time.
You have to update all the time. But that's the whole point of the thing. Can I actually measure these spin fluctuations in real time? And because I might have a model, but it doesn't actually match what's in the lab. So I have this.
For the model, you only have the
the Gaussian thing. That's it. Okay. So this is measuring the actual thing, and then the machine learning algorithm is watching what this is doing, and then applies the pulse sequence that's optimal for whatever noise it's currently experiencing. That's $1.25 million a year project. But then we have NV diamond guy, we have ion trapping guy, we have a superconducting guy. I'm missing one, okay? But we're doing the theory. It said you have to talk about the mitigating dephasing. Okay, that we can do, and it must use machine learning. And I said, okay. I go, why? And it just says it has to have machine learning. So if you don't have machine,
But you assume that when you're using machine learning, you assume there is some certain model you don't know.
You do
But
machine learning or deep learning?
well, they don't know what they're talking about. So we're currently using a genetic algorithm and calling it machine learning.
Just for optimization and search.
Right. So machine learning requires a huge database. We don't really have a huge database. The thing is, so somebody at the Army thought machine learning, we have to put this into the book, so I can sell it to my program manager to fund it. Okay. So, but this is kind of cute, and we've been specifically looking at the NB diamond because it's a nice clean structure. We kind of know what the spins are like. In the ion traps, there's some heating noise. For 30 years, nobody knows where this heating noise comes from. They could be fluctuations on the surface of the dipole trap, and nobody knows. Okay, with this we have a very good idea. It's these spins. Okay, and so
It's really about doing the noise. This is the whole secret.
and I'm not doing anything entanglement here. I'm just measuring the noise and then applying correction pulses. Oh, Howell's here. Good. Okay.
Tell you a secret.
Yes.
I think that putting the one step above is not some quantum computation scientist. I think that maybe it's from experimentalists.
Maybe. Who knows? Hi, John. So I'm so happy. I just finished the classical, and I hand waved my. So now I want to talk about the optimizing overall on all the POVM. Okay, so you can gut me on that one. Where's the toilet? It's down here. All right, it's by the toilet in this building is always by the toilet. This is
Describing it right here.
Oh, we had a laser. Yeah, it's good. So it's good. That was one of the big. It took a long time to get him because we had a service agreement. Yeah, we had a seal, right? That was a part of the deal. For the first time I contacted them in September.
So they actually came now. The still measure there, right? But she was stuck there. It's still running.
Well, we couldn't do it there because there were 4 or 5 experiments on one table. She basically needed the entire table
And now she has it.
yeah, but she gets started next month, so we'll see how that goes. Yeah. I'm glad to have it. It's a really nice place. Really nice place.
least hygienic thing you can do. Owl. A guy had to go to a meeting, so you're in charge of rounding everybody up and being the chair of the session.
It's 10 minutes.
Yes, it's been 10 minutes. I was talking about non-biased estimation. So in this room, nobody sits over there because you can't get to those chairs. So this is a biased distribution. Normally, you would think most people are in the middle and the Gaussian. I only have 40 slides for the. Yeah, but I get another. So each lecture is 45 minutes, so I have to pad it with jokes.
likelihood functions and stuff like that?
No. Because we have people here who have never even taken a course in quantum mechanics, so I have to make it kind of my two favorite co-authors, Hans Wefing and Approximazione. Okay, so I'm uploading papers like my student's PhD thesis, which goes through all of the all of this maximum likelihood and all of this, and so the students who are experts can go and read the details. But for the talk, I'm just trying to give the intuitive picture. So please, you can go easy on me. Okay, you're the chair of the session. Tell them it's time to start.
Start.
Start. Okay.
I'm done fiddling with my phone.
So as you recall, okay.
What's the number of measurements? 28? No, that's
The number of measurements is 28. Okay. My lucky number today. So what's new with you? New is the number of measurements. So this is on the previous slide was n, but today it is new. Ready? Okay.
It's a perfect number. Some of it's all of its divisors.
Yeah, it's a great number, 28. Okay. So we went, I've erased the thing here, but we have, so now we've made it very abstract. I have a box. It prepares probes. They might be entangled or not entangled. I send the probes through the phase shifter or whatever I'm trying to measure, and I make a measurement, okay? And then I have my measurement or dots on this curve, and as I make more and more measurements, I can use Bayes' theorem to update how well I am. This is my estimator, and this is the true value. But instead of using Bayes' theorem from Bayes' theorem, did you know this? You can actually calculate the Fisher information from Bayes' theorem. This is how we do it. Okay, so you write down Bayes' theorem, and then you say, okay, Bayes' theorem says I have a probability I update it each time with the priors. And I take two assumptions. The peak it has a peak, reasonably well peaked, and the number of data points is infinity, and you get the Fisher information.
Reasonably well peaked means it has a finite variance?
Yeah. But the variance still could be very large. Okay. And you get this Fisher information. Okay. And so here, this is supposed to be the quantum Fisher information. It's the classical Fisher information where I've replaced the probability distribution with the density matrix. I argue the density matrix is the quantum. So you know why the density matrix is called Rho? Why is it called Rho? Yeah, that's a good point. The version I heard was von Neumann wanted to write it something like a probability, but P was already in use, so he wrote Rho because it looked like a P. Okay. So whenever I'm lecturing, I'm always writing my P's and my Rho's interchangeably, and the students complain. Okay. But it's an expectation value over this logarithmic derivative, okay? But when you write out the logarithmic derivative, it contains two things. One is this variance, and the other is the steepness of the slope. Remember, the steepness of the slope is always an ingredient. That's all sort of contained in here. So even if you don't know about Bayes' theorem or anything else, you might guess that this is a good way of estimating a parameter. Okay. Now, as I said before, we have the source, we have the preparation, dynamical process, and then we do the detection, and then from the detection we estimate our parameter from the data points. So, as we recall, you could play games in the 1990s where you would change the source, Noon state, M&M state, Yerke state, the twin Vogt state, and then you could change the detection scheme, the homodyne, differencing, whatever you want. So a liberating thing occurred, probably in the past 10 or 15 years, is this idea that, I erased, is that with some very simple physical inputs, a detector must have a certain quantum form, okay? And these are called positive.
Is it recording, by the way?
No. Does it turn itself off automatically?
Is it blinking then?
Oh, it's blinking, yeah. Blinking is good. Red blinking light is good, okay. Right. Okay, so this is called a positive operator valued measure. And it has certain mathematical properties, like the eigenvalues are never negative and all of these things. So the physicist, the lazy theoretician, says, I don't want to talk about what is in Katz's lab, so I want to have some sort of theory of detection. Okay, so we say, what's the most general, physically and meaningful detection scheme I can write down? So each detection scheme we can write down as one of these operators. Okay, that's the key thing. And as I wrote before, they have some nice properties. If you sum all over them, you get 1, which means somewhere in there is Nadav's detection scheme, okay, or combinations of detection schemes and everything else. So when you do this, now there's the third trick that gives us the quantum Cramér-Rao bound versus the classical. You can say, I can now, independent of the preparation, the dynamical process, well, that's not quite true. Given the preparation and the dynamical process, I can optimize over all possible detection schemes without knowing what they are. I know there are 1 on this list, okay? So now I do a maximization procedure and I say, okay, I want to minimize the Cramér-Rao bound, which is the same as maximizing the Fisher information. So I optimize over all of these to make the Fisher information as large as possible. So this is now called the quantum Fisher information, has this additional detection thing stuck in it. And we still get the Cramér-Rao bound is now 1 over the square root of the Fisher information. The square is 1 over this, the delta phi is 1 over the square root. But I no longer care about the detection scheme. It says there is a detection scheme, might be hard to make. It might involve having the detectors entangled or something, but you can never do any better than that. No matter what Nadav crazy thing comes up in his lab, this is the fundamental limit. Okay, so then you can write down a formula that says, okay, now what do I do? I say instead of cooking up any detection scheme and writing a paper, I say I have a number, the quantum Cramér-Rao bound. It's the best you can do independent of any detection scheme. So now I make a list of things that Nadav could do in his lab, and I check them. Intensity differencing, parity measurement, everything else. And I see which one comes closest to the quantum Cramér-Rao bound. And that one I publish because you can't, often we hit the quantum Cramér-Rao bound. And parity, for reasons I do not understand, often is the operator in many of these Mach-Zehnder-like schemes and atomic clock schemes that hits the quantum Cramér-Rao bound. And so once you hit this, you know you can't do any better. So all the papers stop. Right? Nobody's going to write another paper because you can't beat this limit. So that's the idea of the quantum one. You replace the classical probability distributions with quantum probability distributions, but there's this extra optimizing over all the detectors. That adds, for the theorists, it's a relief, because once I compute this, I don't care what the detection scheme. For the experimentalists, it's a heartache, because they go, well, what detection scheme is the one that does best? I don't know. One on the list. There's an infinite number. So we play games going back and forth trying to find these. Okay. So the ultimate precision possible with a given probe state preparation is the quantum Cramér-Rao bound, which is this thing, and the Q means that you replace classical probability distributions with quantum probability distributions, and then you also have this optimization over the detectors. Okay. And that's the best you can do.
So you're saying that if you have a bunch of atomic system and you want to reach your ultimate limit, you measure parity?
No, that's not quite the statement. Okay. You first compute the quantum Cramér-Rao bound, which depends only on your source, how you're going to entangle them or whatever, okay, and your evolution, okay, and then you get a number. So this is the best you can do. Then I pick different detection schemes and see which one comes closest. And just by accident, the parity measurement, which Wineland came up with back in the early 90s, for many of the systems that we look at, always hits this bound, which means...
Parity, you mean the parity of the spins?
Yeah, or in the G8Z state, they're all up, it's even, right? And then, so for the photons, it's easier. 0 plus 2 plus 4, that's even. 1 plus 3 plus 5 superposition, that's an odd parity, okay? So you're measuring even or oddness. Now, parity has other problems. It's kind of susceptible to noise and other things, but at least I can give you one operator and say if you implement this in the lab, this is the, it hits the limit and it's the best you can do. All right. But then now I add noise and loss and dephasing, and then I'm like parity doesn't do so well, and then we say, well, can we modify parity? So this is the game we're playing now. But the beautiful thing is we have this limit that says the limit rules out the crazy Dowling state with the 1 over n squared, right? Okay, which is the crazy Shapiro state. You remember the Shapiro state? Claimed you could get the delta phi is 1 over n squared. This is before your time. There was a big debate about the Shapiro state, and he beats the Heisenberg limit by a quadratic amount, and turns out to be nuts, okay? Which is why I wrote a paper on it too. I just took Shapiro's state, and I just said, okay, I can actually make a state in the lab that's almost has the same properties as the Shapiro state, but their detection scheme was crap. That was their estimator was crap. Now we know you can't ever beat. It's still. Okay, something that, look, when you plug this in and you're talking about possible ranges of the Fisher information, you always get something that looks like 1 over n. So Heisenberg limit is probably the best you can do. But still, Heisenberg limit is now old-fashioned. We don't talk about Heisenberg limit. We talk about quantum Cramér-Rao bound, okay? So 1 over, you remember, Heisenberg's limit is not invented by Heisenberg, and it's not a limit. You can beat it with using two-mode squeeze vacuum. You remember my paper on that, right? Okay. So that's old-fashioned, and that was just a made-up thing. This is some rigorous thing that we think, okay, you can't ever beat this. And often it gives you the Heisenberg limit, but they're not equivalent to each other. Okay. So yeah, the classical, so recap, I have an input, evolution, and detection. That's the classical Cramér-Rao bound. It includes the detection scheme. The quantum, I don't care. It's one of these guys on the list is optimal. I don't know which one, but I don't care as the theoretician. No matter what you come up with in your lab, you can't beat this. Okay, so that's the liberating thing. So asymptotic achievability. This means, this goes back to the derivation of both the classical and the quantum Cramér-Rao bounds from the Bayesian analysis. So it means in the limit of infinite number of data points, you can always hit this. Okay, so then the question is how good you can do with a finite. Unbiased estimator, all of this was for unbiased estimators. Remember, the room is a biased estimator because it's, so you can now modify this for unbiased estimators and do all kinds of stuff. But I wanted to get you a state is optimal if, this is actually, notice the approximation sign, okay? So in my two-mode squeeze vacuum where we beat the Heisenberg limit, we beat it by a small amount, okay? And so it's on the order of the Heisenberg limit. We don't go from 1 over n to 1 over n squared. We go from 1 over n to something slightly smaller than 1 over n, okay? So this kind of tells you that you're never going to get the Shapiro state is crazy and everything else is great.
John, can you go back to that?
Yeah.
An observable is optimal for a probe state if the classical Cramér-Rao bound and the quantum Cramér-Rao bound are equal. I don't understand what you mean by that.
I don't either, because I copied this from Kaushik's PhD thesis.
What does it even mean?
An observable, so the observable, the probe state is what you're sending in, okay? I think the observable is the detector. This is one of the POVMs. That's what the observable is, okay? For a probe state, if the classical Cramér-Rao bound equals, I don't know what that means, okay?
But in practice, if you really want to calculate this thing, you have to go over all possible measurements.
Right.
So you do, normally that means you actually find what the optimal one is.
No. That's the sad news.
Because it could be an infinite number.
Yeah. It tells you this is the best after you optimize over all detection schemes, but it does not give you the optimal detection scheme. So you can run into problems. Okay.
I have a question on this
Sure.
statement about the parity. So you never measure parity. You measure, like say, spins that are up or down.
And then you bin them, and if there's an even number that's...
So isn't that the same thing as saying that the best you can do is measure difference in one spin?
Yeah, so if you, let's go, I'm more familiar with the Mach-Zehnders, okay? So let's go photons and then we can translate via the Rosetta Stone, okay? So one way to implement parity is to have a photon number resolving detector, like a guy has in his lab. So that's measuring individual spins, but it's in individual photons. And so if the photon state comes in and it goes click 2, I say that's positive 1. If it goes click 3, that's minus 1. So I can implement parity by doing single photon measurements, which is exactly what you just said.
And I think you probably should state the reason why that would be considered a parity is because of the Wigner function.
Let's state that now. I was slightly ahead on the slides, and I thought, okay, someone will ask the question, and it will be John Howell. Okay. So the problem is to get a good measurement of parity, you have to take a lot of data. You have to measure all bin, and all of this kind of stuff. And you need a photon number resolving detector or something, which is, they're getting better, okay, but you would like to do something that's slightly different, okay. So I haven't actually talked about the Wigner function, so this is going to make it a little tricky. But I have talked about these distributions in phase space, right? Remember? The vacuum is here. The coherent state is here. You can have a squeezed and displaced vacuum, all of these guys, right? And this is, we call this X in P. Loosely, you're going to hate this. This is, there's one frame where this is the electric field and this is the magnetic field. If you actually look at the second quantization, I like to think of it like this. So you cannot measure the electric field and the magnetic field simultaneously, roughly. Okay, but doesn't matter what this is. We'll call it X and Y. Okay, so you can make these. So what the heck are these blobs? Okay, there's something called the Wigner function, which I'm not going to spend an hour introducing, but it's a function. So let's go back to something we all know and love. Let's call this P and X. I can write down a Wigner function for a harmonic oscillator. Okay? And the Wigner function is a two-dimensional quasi-probability distribution. So when you draw the Wigner function in 3D, the Wigner function for the vacuum is just a little blob centered over here at the origin. And if I project this at the full width half max onto the plane, I get this. This is where it's coming from. Okay? And the Wigner function for a squeeze state, well, now the mountain is, you're right, Nadav, it's right what I'm here. It's squeezed this way, and so that guy looks something like this, okay, when I project it. And then I can put the coherent state, that's a nice round one out here, and that whips around, and that's this. So these Wigner functions, you project them into the plane. I was trying to avoid this, okay? But given any Schrodinger equation, solution to the Schrodinger equation, I can construct this probability distribution. It's called the Wigner function. And this is what I've been hiding from you when I draw these diagrams. And the nice thing about the Wigner function is that knowing the Wigner function, I can completely reconstruct the state. And knowing the state, I can construct the Wigner function. In the lab, and particularly in quantum optics, it's easy to measure the Wigner function. So to measure the Wigner function of an unknown state, I have an unknown state going in here like this. I have a bright coherent state coming in. This is the theorist beam splitter, right? Okay, here. And I do a homodyne measurement, and I essentially adjust the phase and intensity of this guy. But I drew the beam splitter wrong, okay, but you get the point, okay? And then I do something like difference detection here, some other detection scheme. And I can actually, I make slices through the Wigner function. So this is called quantum tomography. So when you go have X-ray tomography to look for a tumor in your body, some cancer, right? They put you in a machine and it shoots little beams of X-rays, okay, which doesn't give you a picture. So there's slices through your body, okay? At each level in your body, there's a little slice. Then you reconstruct the image from the slices using something called the inverse radon-nicodine transformation. Okay, so this is exactly the same thing. I'm making slices through the Wigner function. So there's one slice here, another slice here, another slice here, another slice here. And that's just, those slices are by controlling the phase of the local oscillator. And so you can't, I don't know if there's an analog with spins to do this, but this is the quantum optics way to do this. You can measure the Wigner function, but I don't know what the analog of homodyne is. You would have to actually just count the different spins. So if I know the Wigner function, then I know the state. Now, this is what Professor Howell is getting at. Again, I'm trying to not go down too many rabbit holes in the remaining 15 minutes. The parity operator, so this parity operator, is exactly what you said. Okay, everybody says, well, okay, you're going to have to blah, 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 make all of these spin measurements and Bennett's noise and everything. And then Girish Agarwal, who's now at Texas A&M, I was visiting him and I had a student visiting with him and he goes, and I'm describing this, but I said, you know, and he goes, well, the Wigner function is, at the origin, is equal to the parity operator. And I go, what? Okay. He goes, yes, it's in one of my papers. Okay, so you read Agarwal's paper. So this Wigner function is a function of x and p. And so x and p now, we're talking about x and p in a harmonic oscillator. If I measure the Wigner function at the origin, up to a factor of pi, this is equal to the expectation of the parity operator. Okay, so what's so important about this is that I need lots and lots of slices to reconstruct your body, right? Okay, or to reconstruct any arbitrary Wigner function. But I don't need the whole Wigner function. I just need it at the origin. So maybe with one or two homodyne measurements, I can get the Wigner function at the origin, which is parity for quantum optics. Okay, so you're right. The parity operator, photon by photon, is tricky. Now, Heisenberg does this. There were two experiments where we actually got the super resolution. And one of the, and I talked about this, you implement parity. Heisenberg implemented with photon number counting detectors, Bindum. The group of Ulrich Andersen in Denmark, they did it with the homodyne detection, exactly like this. And homodyne detection, where are my radar guys? Okay, they love homodyne detection. And because this is easy to do, you just need a local oscillator. And in radar, you're not going to be counting single photons anytime soon. And so the idea is you can do this homodyne detection and implement parity.
I don't completely understand this projection, but I think with spins, it would only make sense if you got off the measurement basis, then you'd have some sort of local oscillator locked to the phase of evolution of the...
So this is my atomic clock guy. So what's the analog of a homodyne measurement with spins? I don't know.
That's what I'm guessing.
But in spins, it's pretty easy to measure the individual spins, okay?
Right, it doesn't mean anything. You only talk about some sort of phase once you get off the measurement basis.
Yeah,
you tilt it, and then you have to keep some sort of local oscillator locked to there.
But you don't necessarily want to do that because it's easy to measure spins. But measuring individual photons, that's hard.
You might want to do that to measure energy levels of some sort of spin.
Okay. But in any case, this gives us another road to measuring this. And so for Gaussian states, this only requires one or two settings of the homodyne detector to get the Wigner function at the origin, which gives us parity. This is the answer you wanted?
Yeah, I was just going to say.
Okay, this is good.
The reason why the single photon is an odd parity is because it has a negative value at the origin.
Yeah, okay, so let's draw this. Thank you. You want to teach the one?
Good.
Yeah, okay. So if you look at a single photon, I'm now going to draw the Wigner function from the side, okay? So the Wigner function for the vacuum looks like this. Okay? That's the vacuum. This is just this, now a slice going through the side. If you look at the Wigner function, so this is vacuum, okay? For a single photon, it has wiggles, okay, and then it goes down like this, okay, and this is -1 in some units, okay. So if you measure the Wigner function at the origin of a single photon, which is odd, you get -1, which is the parity, -1 is odd. If you put a 2-photon state, you get wiggle, 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 and then more wiggles there, it goes to +1, okay? So the Wigner function number by number oscillates up and down, and so that's another way to intuitively see why the Wigner function of the origin is giving me the parity photon by photon. So bottom line is that if I want to do some of these super resolution, super sensitivity with parity measurement, parity we think is optimal for many of these schemes. It hits the Cramér-Rao bound, and it can be done with homodyne where we don't have to do photon counting, which is hard at long wavelengths like radar. Okay, perfect. So now I think I'll finish right on time. Okay, so since this is the most math, and then it gets better on Friday, okay? So when we're doing the analysis of the two-mode interferometer, I said the first day, I'm not going to do the Schwinger analysis first thing. I'm going to do brute force calculation of with the Yerke state, you get the Heisenberg scaling. But what everybody does is, remember, there is an analog, the Rosetta Stone, between the Bloch sphere spin, right? The ground state is the ground state of your atom, your spinner. But in the Mach-Zehnder, the ground state just means the photon comes in here and not here, right? That's the analog from the Rosetta Stone. So you can describe the beam splitter, the phase shifter, the second beam splitter as angular momentum operators, just like when I'm on the Bloch sphere and I rotate around this axis and I rotate around that axis and I rotate up. You have angular momentum operators, which you can write down. By analogy, you can write down angular momentum operators for the Mach-Zehnder interferometer. Okay, and this is called the Schwinger representation. So you have JZ, which is my favorite. This is the intensity differencing operator. Remember, okay. A dagger A is and B dagger B, the difference in the energy. JX is gives you off diagonal terms, that's why we're measuring sigma x, right? That's where the phase is accumulating. And then JY, that's the input photon number difference. So Schwinger came up with this nice way to describe Mach-Zehnder interferometers. So if you're a theorist, this is nice because you have these angular momentum operators. And so each element is just an operator. There's your beam splitter. This is your phase shifter. And you just multiply them together. So you make a very complicated interferometer. Each beam splitter has one of those. Each phase shifter has one of those. The mirrors are essentially the identity. So by simply multiplying these operators together, you can get quickly the answer because I'm a lazy theorist. Okay. So it's a little confusing because, like, if I have a twin Fock state, N1 and N2, in the J notation, it's N1 over N2, Mz. So this is like angular momentum notation. But using this, you can calculate things quickly. And the other point is that when we talk about Kefir, did you move again? Yeah. So why do you call your interferometer an SU11 interferometer?
It's represented by a group of SU11.
Good answer. You just repeated what I said back to you. Okay. All right. So why is this called an SU2 interferometer? Because this algebra is the same as a spin on a Bloch sphere, which is the SU2 group for group theory. So everybody was puzzled. Why is this the SU2 interferometer? In the Wigner, in the Schwinger representation, it looks exactly via the Rosetta Stone like a Bloch sphere, and that's SU2, so this is SU2. Now, Kefir has a different problem where he replaced the Mach-Zehnder interferometers with squeezers, okay, and then you have to redo the beam splitter operation. Now becomes an active squeezing unitary element, and instead of getting let me rephrase this carefully. Instead of getting sines and cosines, which we get with the linear Mach-Zehnder, you get sinh hyperbolic sine and hyperbolic cosine. And you look this up in the big book of group theory, and you go, that's an SU11 group. And so when they write, this is an SU11 interferometer, everybody goes, what the hell is that? Okay, it's just the group theory in this representation. But in any case, you can go through the phase estimation, and again, this goes back to Mandelstam Tom one more time. So this is the Heisenberg equation of motion for any observable A. And this is also in Griffiths, right? Professor Heisenberg, who is a vacuum fluctuation. Okay. So the evolution, okay, is just given by, well, in the old case, this would be the Hamiltonian, but now this is JZ, which is my operator that I'm using here. So you take the commutator, you expectorate it, and then that gives you the derivative of A. And expectorate in English means to spit, but I use it to mean take the expectation value of, and my students laugh, and the other professors hate me. They also hate me about Dowling's constant as well. You missed Dowling? Okay. So anyway, so this is related to the speed limit. Before we had the Hamiltonian here, now I have JZ, which is the evolution operator. But there's a certain speed, and this was d by dt, now it's d by d phi. When you have this kind of evolution, you can accumulate phase only at a certain rate. You're limited by the Hamiltonian evolution, which is guided by this commutator. So now when I do the uncertainty principle, I run the whole thing through. If you look at Griffiths, the general uncertainty principle is you have two operators, okay, that don't commute. You take this guy times this guy. It's always greater than 1/4 over this whole thing. Now with delta x and delta p, this is just a constant, but for angular momentum, it's not. But then you take this, insert this over here, okay, and then, you know what's going on here, you run it through a few lines, and you get this guy is equal to 1/4 delta jz. So delta jz is the equivalent of delta Hamiltonian energy spread. So you want to make this spread as big as possible, and this coincides with the quantum Cramér-Rao bound for the pure states. So this whole quantum Cramér-Rao bound argument, you can also reproduce it with the simple quantum speed limit arguments in certain cases for pure states.
So is that 2 or square root of 4 important? Observable? Or is that just...
The 4?
Yeah.
Don't worry about the 4. Usually, so
one?
4. 4 is 2 squared. 2 I've already defined to be equal to 1. So this is showing up from this particular definition of the, the uncertainty principle, so that it matches the delta x delta p definition, and you get the right constant. But in every book it's like delta times x times delta times h. Sometimes it's greater than equal h, sometimes it's greater than equal h bar, sometimes it's h bar over 2, and people argue which one it is. Okay, so I'm not so worried about this. But this is the important thing, because this is the spread, and delta jz is the number difference between the uncertainty and the number difference. Remember, Nguyen states, n over here, nothing over here, n over here, nothing over here. That's the biggest delta jz you can get, and that gives you the Heisenberg limit. But if you send the guys through one at a time, then the delta jz isn't so large, and you get the shot noise limit. Bah! I hit the mute button. All right, so I'm pretty much done. I don't know how much I did extra stuff, blah, 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 blah. What am I going to say here? Okay, this is something that we did quite a while ago. By staring at the Schwinger notation long enough, if you're a theoretician, you can ask the question, what are the states that are optimal for photon counting, okay? And there's something called path symmetric states, and it's defined by this equation. So you read Kaushik's, it's in this paper, it's in Kaushik, not Kaushit, okay? So Kaushik comes from a part of India where they have a religious tradition where they take dried cow dung and cook it with incense, and they put it on their foreheads. And he said, yeah, in school they always called me Kaushit, even the Indians. Okay, so anyway, Kaushik. So the point is, you have this equation, and what is a path symmetric state? Everything we have looked at so far is a path symmetric, the Yerke state, the Nguyen state, the M&M state, the coherent state with a vacuum, coherent state with the squeezed vacuum. They're all path symmetric states. And then you can show that by photon number counting, you can always get the quantum Cramér-Rao bound. But in most cases, the photon number counting can be replaced with the parity. Okay. And so, depending on what your detection scheme is, and so, you know, there might be other detection schemes that hit the quantum Cramér-Rao bound, but once I find one, I just say, I'm not going to keep looking. How do I actually implement this in the lab? Okay, and that's the whole discussion with the Wigner functions. And there's your parity operator, and this is the shot noise limit, and we're showing this is squeezed vacuum, and this is anyway. These are different plots in the paper. This is the phase resolution. This is the super resolution, and this is our scheme. This is Plick, Dowling, and Agarwal. Well, the parity operator can always be implemented measuring the Wigner function at the origin with homodyne. So this ain't your grandma's homodyne. Okay, so when you guys from ELTA, like delta with an E, okay, I have a box that says the quantum homodyne detector. Okay, so a homodyne detector is like one beam splitter and one local oscillator. Okay, you replace it with this thing. There's a phase controller and some extra stuff in here. Okay, and you have 4 detectors instead of 2. So it's homodyne, but not your grandma's homodyne. It's just something a little special. And the promise of this is that if you do this at high power, you get the super resolution. But at high power, you guys don't care. You can easily beat Rayleigh. At low power, you get the Wigner function at the origin implemented by...
My grandma has a homodyne just like
your grandma. Well, your grandma's special. We know that. Okay. And but you implement this instead of regular homodyne. You get the parity at the origin. You get the Wigner function at the origin, which is parity. In the few photon regime, we only get a few return signals, and you beat the Rayleigh diffraction limit. All right. And 40. And I'm almost right on time with including the break. It's actually 2 45-minute lectures with a break. So depending on the break, I should end at 5:45, but there was a break, so I'm a little ahead. Oh, okay. So this is the most, I don't want to scare everybody away. So this was the most mathy thing. So you were not here for the debate. So a guy says, look, you come and give some lectures, and the Hebrew University will pay all your expenses so I don't have to, and then we can work. Okay. I go, that doesn't sound bad. And then 14 lectures later, 14 hours of lectures, I'm nearly dead. And then Barak Dayan says, here you're giving lectures at Hebrew University. Weitzman is jealous. We want lectures at Weitzman too. And I said, okay, maybe one at Weitzman. And then Ave Per says, well, if you're going to Weitzman, you have to go to Bar Ilan. Okay, so I'm already giving 14 hours of lecture. And then their idea is put me in a taxi every day on the day I'm not lecturing and ship me across Israel to give even more lectures. And then Avi says, this was the killer. He goes, and you can go on the lab tour. And I said, no, okay. So I Skype with Barak once a month. And I said, I need Dowling's pit bull. I'm not going to Weitzman. I'm not going to Bar Ilan. I'm not going to get into a taxi and go anywhere. I'm not going to go on a lab tour. And I'm not giving any more lectures. And if people want to come to talk to me, where's Yaron? You have to come to where I am sitting, okay? I don't care how good your coffee is, okay? Because I'm already doing all of this other stuff. And so there was a debate. How much more jobs could we give Dowling before we kill him? Okay, this is between Barak, a guy, and so I'm not dead yet. Superposition. But the problem is, if I go through the beam splitter, if they measure me in Bar Ilan, I collapse. Dead or alive. That's only a 50-50 probability. So after the negotiations, this is Israel, so negotiations go on for a month. They said, okay, instead of giving extra talks at Bar Ilan and Weitzman, what you're going to do is give a talk on Israeli Friday, Thursday, that is a review of everything that you talked about already, okay, which is crazy. So I said, sure. So what I'm going to do on Thursday, since they haven't come to any of the other talks, they won't know that it's not a review, okay? So everybody is coming from Bar Ilan the mountain must come to Muhammad, the old thing. Okay. So after all of the discussions, they're all coming down on Thursday. Which room will it be in, this one or the other one?
No, the other one.
Yeah, okay. So there's going to be Bar Alan and there's going to be Weitzman, and they think they're getting a review of the entire course. But that's not true because it's unfair to you guys who signed up. But I'm going to do something fun where I'm going to talk about quantum networks of quantum sensors, which is, this is hooking the quantum sensors LIGOs with instead of a kilometer long arm, a several thousand kilometer long arm. Imagine making a phase array of LIGOs to detect gravity waves, or a phase array of optical telescopes over distances equal to the Earth's diameter, okay? So now, the first step is, what is a quantum sensor? You now know that. So then the second question is, how do I hook them up? And you need a quantum internet. So I recommend you buy my new book when it comes out, which is titled Schrodinger's Web, The Race to Build the Quantum Internet. Now, in the file is my previous book, free PDF, Schrodinger's Killer App, Race to Build the Quantum Computer. So that's almost done. We've got Google and IBM fighting over who's got the best. So the quantum internet is the next new big thing. And the question is, what are you going to do with the quantum internet? Well, you can hook the sensors together. So we're going to make gigantic sensors the size of the Earth. We put them in orbit. And the Chinese are talking about making entanglement between Earth orbit and lunar orbit. So now I have a synthetic aperture that's the diameter of the moon's orbital radius around the Earth. What can I do with that, John? Gravity waves from the cosmic background radiation. You can measure this. So everybody knows cosmic background radiation. So there's this big bang, boom, and there were these photons, thermally emitted photons. And then they became redshifted over 14 billion years. And now the photons are microwave corresponding to a temperature of 4 degrees Kelvin, and you can see it with a radio antenna. And you win a Nobel Prize. Okay. But they started out not at 4 degrees Kelvin, they started out at billions of degrees Kelvin, but the expansion caused them to cool. So every quantum field, should have been produced in a thermal state at the Big Bang, including gravity waves. So the theory says that there is a cosmic background radiation, not of photons, but of gravitational radiation, okay? So the LIGO is specifically designed to see these inspiraling black holes. The wavelength of those is approximately the wavelength of the LIGO arm, and everybody in ELTA knows if you want an antenna, you build the antenna dipole length the same length as the wavelength, okay, for efficiency. But some of these long wavelength remnants from the cosmic background radiation of gravity waves are huge, about the diameter of the Earth. And so people talk about how could you see such things, and so I will give you the most crazy idea how you could do this on Thursday. Okay? And that'll be the end. And so, who is registered? So you have to send me a one-page, what I learned from reading one paper, okay? And don't worry, I probably won't read it, okay? But you have to send this for your grade. And a guy suggested, when is the final exams? It's not for 2 weeks, right?
Yeah, exams started 2 weeks.
Exams started 2 weeks.
In a day.
So when do you have to post grades?
10 days after that.
So what date would that be?
Around February 5th.
That's when you have to post grades.
Well, if the exam is on 10 days after the exam.
Okay.
Whenever it is.
So I want the reports by January 31st, because I have to pretend to read them for 5 days and then figure out how I'm going to post the grades even though I have no access.
Send them to Chagai.
Yeah, I will send them to Chagai. Okay. But I need at least 5 days between when I get the reports. I will actually read them, unless they're in Hebrew. I'm not taking off credit if it's badly written English, but your English is probably better than mine. Okay. So that's the plan. So you're going to see all these bewildered people from Weitzman and Bar Ilan wondering what the heck is going on, and you know the joke. So John, thank you. You going to dinner? No. Yes.
I just asked my wife
Nadav, you going to dinner?
I still don't know.
Yeah, okay. They're in they have to ask the boss if they're going to dinner. Now, I'm not going to dinner with Elta, right? That's off the table.
That's on Thursday, maybe.
We're going to meet on Thursday before the talk. 2 o'clock. That I know. That's on my calendar. Okay.
Now we have to demand dinner from Elta.
I've had plenty of dinners, okay? I don't need any more dinner.
supposed to tighten with extra force.
Yes, sir.
Cramér-Rao bound. The Cramér-Rao bound, is it tight? I didn't understand. I wasn't sure.
It's tight. It's tight.
So
if you violate, okay, there's some tight is okay. So I'll give you an example where people were cheating. Okay. So you optimize over all possible detection schemes, right? Could be a homodyne, anything you want. So people were doing something like this, where they prepare some state, okay, and psi, and some entangled state A, B, and they send it through the phase shifter, okay, and then over here they optimize over all the detection schemes, okay? And they were getting better than the Heisenberg limit. In one case, they got infinite precision. Delta phi is equal to 0, okay? So that's crazy, okay? So, and I refereed the papers and said, this is crazy, but I don't know why, okay? The problem is that a perfectly acceptable POVM is a homodyne measurement where I take the state psi and mix it with the local oscillator alpha of infinite power. Okay, if it's infinite, then it's not a POVM. But if it's for any non-infinite number that's large, okay, so he was finding this when you optimized over this. So this is a hard limit. However, if you had an infinitely powerful local oscillator, you would just put it in the front and screw with that, just like LIGO does, and use that, okay? So this was we found out people were cheating, okay? So now we have a way where we can do phase, we call it phase scrambling, which kills off this kind of cheat, okay? So it is tight if I have an infinitely powerful laser, okay? But you know, so now when people write a paper, even I am guilty of this. I published a paper where I calculate quantum Cramér-Rao bound and say this is the best you can do, and it turned out to be wrong, okay? Because not quite infinity, but there was local oscillators. So now when people write a paper and say we have the quantum Cramér-Rao bound, this is the best you can do, I go, you must give me a detection scheme that hits this, okay? I will not accept just the result. It is tight, but the detection scheme might be unreasonable. So you cannot publish anymore with the quantum Cramér-Rao bound alone. You must provide a detection scheme. And half the time it's parity. I don't know why. So it's tight, but there's a way to cheat. Are you happy? Too much math?
No,
it was okay.
I didn't understand quite if when you talk about detection scheme, do we assume that the state we insert must be in eigenvector?
No, it can be no. So it can be some arbitrary superposition or any crazy thing.
So why wouldn't the optimal detection scheme would be the one that the state we insert is the eigenvector of?
Eigenvectors are overrated, okay? So, can you turn, is this off? You push the power button twice, so it goes off. Otherwise they get mad. Hold the power button down. Yeah, I remember. So, an eigenvector of the electroharmonic oscillator is this. So I could send a Fox state, okay, through a phase shifter, and then I get e to the I 10. Okay, that looks good. But the problem is this is just only in one arm. There's no reference thing. So if you run the Cramér-Rao bound for this, you get 1 over square root of n. You don't get any improvement, even though